Welcome to the solutions to the Regents Physics Dynamics problem set, problems number 19 through 23. The topic shift you should definitely see in this group of problems was moving to discussing momentum. So there's going to be quite a bit of learning here in this set of problems. We'll start off with number 19, which asks, can a bullet have the same momentum as a truck? And explain. Momentum is the characteristic of an object that is a product of its mass and velocity. One of the most common misconceptions is that momentum is a force. Momentum is another one of those words that has many different contexts, many different meanings, that is, and depending on the context in which we're using that word. But in physics, momentum is the mass of an object times its velocity. Objects that are more massive and also have velocity have much greater momentum than small objects that have that same velocity. The question here is, can a bullet have the same momentum as a truck? Well, the bullet has small mass, but it has large velocity. So if we multiply those two, we get the momentum of the bullet. The symbol for momentum is lowercase p, and you already know your symbols for mass and velocity. Over here at our tractor trailer, this truck has a large mass, but relative to the speed of the bullet, it has a low velocity. So the velocity of the truck is small. So the truck's momentum would be the product of its mass and velocity. And you can see that it would be possible, theoretically, to have the momentum of a bullet and the truck be the same because of the difference in the mass and the difference in the velocity. It is possible. Number 20, why are cars made with bumpers that can be pushed in during a crash? The concept that this addresses is the impulse momentum theorem. If you would go to your reference table, you will find that in the mechanics section, J equals F times T, which equals delta P. That is the impulse momentum theorem. And the impulse momentum theorem says this, that the force that acts on an object times the time in which that force acts causes that mass to change its velocity, or in other words, change its momentum. You see a delta in front of the P here, J being the symbol for impulse, lowercase b the symbol for momentum. If there's a delta in front of that P, that means one of the two things used to calculate P also had to change. Well, in this particular case, it is a change in velocity. There are many applications for the impulse momentum theorem, most of which are related to safety. There's also sports applications, which we may discuss at some later time. But in this particular problem, car safety is the issue at hand. Now, you can see in this car on the left that this car went from some initial velocity to rest in a very small amount of time, neglecting the fact that maybe a chunk of it fell off here or there during the crash. The car's mass does not change. And no matter if this car ran into a pole like it did here, or ran into a wall, ran into another car, let's say it was going 60 miles per hour. It ended up at rest, so the change in velocity, no matter the situation, would be the same. It's still going from 60 miles per hour to rest. But in this car safety application, what happens here, as you take a look at this picture on the right, is that the car has what's called a crumple zone that absorbs some of the impact. And what that does is it increases the amount of time over which the force acts on the mass. So by increasing the amount of time, and on the right hand side here, the mass of the car and the change in velocity doesn't change, the result is that it decreases the force that acts on the system in the process. So by increasing the time over which the force acts, you actually decrease the force. This is the same as the airbag, okay? By the driver impacting the airbag here, what's happening is that driver is going from whatever speed the car is going to rest. And what the airbag does is it increases the amount of time over which the force is applied, therefore decreasing the force. So that is the safety application of the impulse momentum theorem. Number 21, you are sitting at a baseball game when a foul ball comes in your direction. You prepare to catch it barehanded. In order to catch it with the least amount of pain, should you move your hand toward the ball, hold it still, or move it in the same direction of the ball at impact? Explain your answer. I went on and picked out a picture here of a fan catching a foul ball. But what I want to focus on is this guy right here who is preparing to catch it with his bare hand. These two fans have brought gloves to the game. We'll address her in a moment. Okay? Let's focus on the guy here in the middle who is going to use his bare hand. Now, in all three of these cases, this ball has a certain velocity at impact with this glove, or if it was this glove, or if it was this guy's hand. The mass of the ball is not going to change, nor is the mass of their hand, hopefully. No parts removed. So, no matter which person catches the ball here, all three have the ball undergo the same change in velocity. That is, it's going from some speed at impact to rest, and the mass of their hand is not going to change. Therefore, the pain related in the question here is directly related to the amount of force applied to the hand. So the goal here would be, again, just like the car safety question above, increase the amount of time over which the force acts to decrease the force that acts on the object, in this case the person's hand. So if this guy were to end up catching the ball, he'd want to give with it as he catches it, or in other words, move it in the same direction of the ball at impact. What this would do was increase the amount of time over which the force is applied to his hand, therefore decreasing the force that's acting on his hand and reducing the pain. Now, this woman came prepared. Not only did she bring a glove, but she's got a little helmet on her baby that she's holding in her arms while she catches the foul ball. That's dedication. Moving on to number 22. Your brother's mass, 35.6 kilograms, so M, and he has a 1.3 kilogram skateboard, so another mass. What is the combined momentum, so P, of your brother riding his skateboard at a speed of 9.50 meters per second? And we know that's V. Momentum is mass times velocity. They want the combined momentum, so we need to combine the mass. So 35.6 kilograms plus 1.3 kilograms. And the speed is 9.50 meters per second. Adding these two and then multiplying by 9.50 gives us a momentum of 350 kilogram times meters per second. The unit of momentum is kilogram meters per second. In 23, a hockey player makes a slap shot exerting a constant force of 30 newtons on a hockey puck for 0.160 seconds. Force F, 0.160 seconds, time T. What is the magnitude of the impulse given to the puck? Impulse, capital J, is the force times the time over which that force acts. The force was 30 newtons. The time was 0.160 seconds. Multiplying these two, we get 4.8 Newton seconds. The unit impulse is Newton seconds. At some point, we'll show from the impulse momentum theorem why the Newton second and the kilogram meter per second are the same and interchangeable. There's your introduction to momentum, impulse, and the impulse momentum theorem. Much more to come as we'll tackle questions 24 and 25 in class tomorrow.